LHC going, and there's a slight concern on my part that I'm going to be crucified upside down for continuing to put my faith in the LHC, but I'll try to give you reasons today why I think this is really an exciting endeavor. So I just want to touch on a couple things in today's talk. Obviously, there's a lot of things that have gone on during the first run of the LHC, but there are sort of two central things that are most interesting to me. You notice I haven't listed supersymmetry among any of these things. Supersymmetry is very interesting, and the LHC has done a very good job of probing it. I don't have a whole lot to say about supersymmetry in this context. So what instead I want to focus on are, of course, the most exciting thing that's happened at the LHC during the first run, which is the discovery of a standard model like HIGGS and our ongoing exploration of the HIGGS sector. The other thing that I think is very interesting and important and is growing in significance going into the second run is the question of dark matter at the LHC, how efficiently we can probe particularly weak scale dark matter, and what the prospects are there. And then finally, I just want to end the talk with a little bit of the blog report, which is to say, what are the things, the general sense you get from the LHC is that apart from the HIGGS discovery, it's all just null result after null result. That's not actually entirely true. I think there are a number of searches that have interesting anomalies that are consistent with all other parallel searches that have happened. And so these are things that, at least in my mind, are worth keeping an eye on as we continue to analyze run 1 data and think about moving into run 2.
What is a sensible anomaly?
What is a sensible anomaly? A sensible anomaly is one where there are excesses in multiple channels, right? So as opposed to one bin being high, successive bins in a distribution being high. They're consistent with other, there's some model interpretation of the excess such that that interpretation is consistent with all other direct searches. So for example, if one excess is only explicable by light leptons that have to live beneath the LEP bound, that's not a sensible anomaly. But if it's light staus, then that is a sensible anomaly. Okay, so there are, I would like to believe I have a relatively decent standard for sensible anomaly, but you can let me know if you disagree. Okay. So just to start with the HIGGS sector, obviously this was the most important and exciting thing that's happened at the LHC during the first run. I like to show the New York Times front page for a couple of reasons. One, because Dennis Overby was reporting from Aspen, not from Geneva, but also because this captures the sort of sense of hyperbole about it, the key to understanding why there is diversity in life in the universe. This may be a slight overstatement, but at least it captures the sense to which this has been an incredible and very important discovery. So what have we learned about the HIGGS since the discovery, in particular since the discovery announcement on July 4th, 2012? Well, one thing we've learned that's become particularly concrete in data that we've gathered actually since then, particularly the last part of the first run, is it really is about 125 GeV. And the reason why that's an interesting statement is that actually the central value of we had a pretty good idea of the mass when the HIGGS was first discovered, but the central value of that mass has differed between the collaborations. At Atlas, famously, they had discrepant measurements of the central value of the mass that were disagreeing to a fair bit at one point. I think at this point that's all calmed down quite a bit, so we know pretty well that the mass of the state is about 125 GeV. And the way that we do that, of course, is to use the two resonant fully reconstructible channels. Okay, so that is to say, there are decays of the HIGGS such that once you measure the products, in the decay products in the final state, you know the exact kinematics of that final state, and you can use that to infer, based on the invariant mass of the decay products, you can use it to infer the mass of the particle that decayed. And so these are the things that we use to get a measurement of the HIGGS mass. So in particular, the decays that are fully reconstructible are the decays of the HIGGS to 2 photons, and then the decays of the HIGGS to 2 Zs, one of which is off shell, and those both go to 4 leptons. So with those exactly reconstructible final states, Atlas and CMS both have their best shot at the HIGGS mass measurement. So Atlas, HIGGS to ZZ is a little low, HIGGS to gamma gamma is a little high. The central value comes in right at 125.36 GeV. CMS, the story is flipped. Gamma gamma is a little low, ZZ is a little high. These circles, of course, this axis then is relative to the signal strength in that channel relative to some standard model normalization. Okay, so that's the extent in this direction. The extent in this direction is just the resolution of the mass measurement. But they both have pretty good agreement. I think CMS is now at pretty much 125.05. So there's very good agreement to within 1 standard deviation measurements in the 2 different mass resolution channels agree. And then you can see some other systematic behaviors. Atlas in general, the signal strengths are a little high. CMS, the signal strengths are pretty close to the standard model expectation. There's really not significant difference in the mass that you resolve from the gamma gamma and the 4 lepton channels. Really within one standard deviation, they give you the same thing. The other thing, of course, we know apart from the mass is it really is the HIGGS in the sense of being a standard model HIGGS. So recall what's beautiful about a standard model HIGGS, that is to say one single electroweak double degree of freedom that is responsible for giving mass to all fermions and massive gauge bosons in the Standard Model. Under the hypothesis of the Standard Model Higgs, all of the couplings actually of the Standard Model Higgs, all of its production modes, all of its branching ratios are fixed once you know its mass. And that's because, again, the hypothesis that it's just the fluctuation around the vacuum expectation value that breaks electroweak symmetry. That means that that's precisely what's imbuing mass to all fermions and gauge bosons. So that precisely fixes the dimensionless coupling of the Higgs to those degrees of freedom. Okay? And so this is the hypothesis of the Standard Model Higgs. This is really what we're testing in all of the coupling measurements that we make of the Higgs moving forward. And what you see is really astonishing agreement with the predictions of the Standard Model. So a nice way to plot this is to say, we have massive degrees of freedom in the Standard Model. These are the 5 most massive, the taus, bottom quarks, WZ, and the top. The mass of these degrees of freedom is supposed to be proportional to their couplings to the Higgs. So this is the inferred coupling of these particles to the Higgs. For fermions, it's just directly the couplings. For gauge bosons, it's an appropriately normalized dimensionless coupling. And so you can ask the question, so this is the line that the Standard Model prediction gives you relating the mass to the coupling. And you can ask now that we measure, we can infer the coupling of the Higgs to these various states at this sort of 68 and 95% confidence level. And you see they line up really, really beautifully with the prediction line. Okay. So this is the statement in a nice graphical sense. This is, to the precision that we know of, the Standard Model Higgs. You can break down these predictions or observations into lots of different channels in which the measurements are actually made. And so in particular, in general, there are several different production modes of the Higgs that can be identified through tags involving the initial state. And then there are various final states of the Higgs that also can be identified accordingly. And so those combinations of various production and decay modes allow you to separately pairwise identify lots of the different couplings of the Higgs to Standard Model states. And so this is just some enumerated list of all the best measured channels. Higgs decays to bottom quarks produced in association with some Standard Model particle. Lots of different possible Higgs decays to photons with various production modes. Higgs decays to W bosons with different production modes, taus, and Z's. And you can see for all of them, basically, the production rate times branching ratio for all these processes lines up very well with the Standard Model prediction, which is, this is normalized to Standard Model. So here's the one line. And you can see that all these measurements, with the exception of one measurement, that's the top associated production of the Higgs with decay to WW, it's a bit discrepant. Everything else agrees within one standard deviation for CMS. And the same is true of Atlas. So this is a really beautiful illustration. This is really lining up in the way that we expect from a Standard Model Higgs within error bars. I'll get to this a little bit later when I get to the anomaly section of the talk. That's right. So there's also a sociological question, which is, to what extent is this agreement too good? Okay, and so I haven't computed the significance of the excessively good agreement between the observation and the prediction. But I think there's a general concern, and I'll comment a little bit about that concern later on, that knowing the answer for the Standard Model Higgs certainly is providing a focal point for measurements. And in fact, we've seen the thing that's most disturbing is that we've had about 1.5 years to analyze the end of run 1 data. And so there have been actually multiple analyses of the same data set that get refined over time. And all of those analyses have the property of converging towards the Standard Model prediction. So even with the same data set, the legacy analyses of the run 1 data have converged more closely with Standard Model predictions. So I think, as a theorist, that's a slight object for concern. On the other hand, the experimentalists are doing a very good job. And I don't think anyone can accuse them of any active systematic bias. Just one thing I want to say, though. It's actually not insanely surprising that there's such good agreement with Standard Model predictions, in a sense that, of course, hindsight is 20/20. But we really kind of knew, before the Higgs discovery, where the Higgs had to be if there was an elementary Higgs scalar, and to a good approximation, what its couplings had to be, at least its couplings to massive gauge bosons. And the reason for that is, before you discovered the Higgs, there were sort of 2 indirect observables you had to probe new physics in the electroweak sector that might be relating to the Higgs. These are the famous oblique parameters, the S&T parameters. And you could measure those just by making measurements of other Standard Model production and decay modes, other Standard Model properties. You can place constraints on new physics contributions to the S&T parameters. And crucially, these S&T parameters, they depend both logarithmically on the mass of a physical Higgs boson in the Standard Model, and also if that Higgs has different couplings to vector bosons than what is prescribed by the Standard Model, that also actually shifts its contribution to S&T. And so the fact that S&T were fairly well measured prior to the Higgs discovery, and the fact that we had non-observation of the Higgs both at LEP, which was able to rule out Higgs masses at low mass, and also at the Tevatron, which is able to exclude Higgs masses right around resonant production of massive gauge bosons, that sort of gave us a window where precision electroweak measurements were pushing us. And so this is actually a plot by Jens Erler that was a little bit of a post-diction, but just saying, given that we know where the Higgs is, ask if we looked at the Tevatron data and LEP data, so existing collider experiments, and also inference from precision electroweak, you can sort of construct a likelihood for where in mass you would expect the Higgs to be. And that distribution is peaked. Okay, it's peaked a little bit lower than 125. So here's 125. It's peaked around 120. But that's a very strong statement that you really did expect the Higgs to show up around 125 GeV. And then the other statement you have is that if you just look at electroweak precision tests, so again, measuring these oblique parameters before you even had a physical fluctuation of the Higgs, the fact that if that Higgs coupled to massive vector bosons differently from the standard model prediction, that would actually show up in contributions to these electroweak precision observables. That actually allows you to constrain just from these oblique constraints that we already had before discovering the Higgs. It basically tells you that the coupling of the Higgs to massive vectors, so this is that coupling normalized to the standard model prediction, had to be fairly close to 1. It had to be within about 5% of 1 for a standard model Higgs around 125 GeV. So of course, it's amazing we've discovered the Higgs, and it's very impressive that the couplings are all agreeing so well with the standard model prediction. But it wasn't entirely unanticipated. We knew from everything I think we had beforehand, we at least had a pretty good ballpark for where it would show up. That's where it showed up. And we also knew that its couplings, at least to massive vector bosons, would have to be pretty close to the standard model prediction. Okay. But that aside, one of the things that's been beautiful about Run 1 is how impressively covered the Higgs production and decay modes have been. So the Higgs has 4 primary production modes at the LHC. It can be produced through gluons, through what we call gluon fusion. It can be produced through what we call vector boson fusion. That involves production of massive gauge bosons that fuse to produce a Higgs. It can be produced in association with a vector boson, or it can be produced in association with top quarks. So we can measure in all these different channels. We can identify those unique production modes. And then we can look at the possible decays of the Higgs. So these are sort of ordered in terms of their size, decay modes of the standard model Higgs at 125 GeV. Bottom quarks, Ws, gluons, taus, charm quarks, Z bosons, photons, Z and gamma, and then muons. And so in many of these channels already just in Run 1, in blue, I've sort of shown things that we've measured with high precision, individual channels with high precision. These are the most distinctive channels. But then there are also many channels we've had sensitivity to in Run 1 that we've measured with at least some degree of precision. And as you can see, this is already covering sort of a large swath of the possible production and decay modes of the Higgs. And I think when we turn on the LHC next spring for Run 2, we're going to be able to cover a lot of these very rare modes. And so all that's going to be left behind are sort of the very hard to characterize modes where the Higgs is produced in an indistinct way, and then it decays to things with strong interactions that are very hard to distinguish from QCD backgrounds. So there are a couple of sort of holes that are going to be hard to cover in the Higgs search strategy, but just the takeaway message is we've already managed to cover an astonishing number of the production and decay modes of the standard model Higgs. We're going to get more when we go to Run 2, and this is just a great testament to the performance of the machine and also the awesomeness of the standard model Higgs. So some of the specific details we've learned, you can measure lots of things. Once you make all these measurements of production and decay modes, you can ask lots of questions just by doing combined fits to the standard model couplings. And so one thing you learn is that its couplings are custodially symmetric, which is to say it couples the same to W and Z bosons according to the predictions of the standard model. So you can make that measurement just by measuring its coupling to W's and measuring its coupling to Z's, and then taking the ratio of those couplings. So that's what they call this variable relative to the standard model. So standard model, these would appropriately normalized be unity. And you in fact see that at least within good precision, based on coupling fits that we have right now, profiling over all of the other possible couplings to standard model states, we're in pretty good agreement with the standard model prediction. And this actually wasn't necessarily even guaranteed. I told you we had precision electroweak measurements prior to discovering the Higgs. One of the things that precision electroweak measurements tell you is that custodial symmetry, this sort of symmetry relating W and Z, is a good symmetry of the standard model. But this actually could have been different from, so that tells you actually at a good approximation this should be true. But even so, once we discovered the Higgs, the couplings to W's and Z's could have actually been different, still consistent with that measurement. So this is a nice thing to see. Another thing you see, you could ask maybe the Higgs somehow couples to up-type fermions and down-type fermions differently. You can certainly write down theories where that's the case, but you can go ahead and make the measurement of the ratio of couplings to down-type fermions like B quarks versus up-type fermions like top quarks, and the answer is that it slams on standard model prediction. Okay, so. How is that measured? So what's measured, it's just what they do is they do a combined coupling fit. So they take all of the production and decay modes they've measured, right? There's a standard model. What you take is the standard model functional form for those couplings, and then you allow the magnitude of that coupling to a particular state to float. And then you just do a combined fit. In this case, what you do is you pick 2 couplings that you want to measure, and you profile over all the other ones. Yeah. Oh, so this is inferred. So good. So you get a handle on bottom quarks directly because the just decay mode into bottom quarks. Also, you get some inference because, of course, bottom quarks do contribute to gluon fusion. And then the coupling to up-type fermions you get primarily from the top. So we have both associated production of the top quark and also its inferential contribution to gluon fusion. Okay. So that's interesting. Another thing you learn that's very interesting is it's not obviously coupled to loops of new physics. So something that I think the Higgs was a promising object to probe, certainly before and during its early days of discovery, was there are some couplings in the standard model of the Higgs to certain final states, in particular the massless gauge bosons of the standard model. Those couplings are not induced at tree level, because of course these gauge bosons are massless and the Higgs is coupling to mass, but they are induced in the standard model at one loop. So famously, the Higgs coupling to pairs of photons and the Higgs coupling to pairs of gluons, these are induced through loops in the standard model of standard model degrees of freedom. So in the case of the coupling of Higgs to photons, it's through loops of top quarks and W's. In the case of Higgs coupling to gluons, it's through loops of top quarks. But if you had additional degrees of freedom that had standard model quantum numbers, so for example in supersymmetry you have lots of additional scalar degrees of freedom that carry standard model quantum numbers, those degrees of freedom can run in loops and they can couple strongly to the Higgs, and they would actually interfere with or contribute to the standard model predictions for these loop-induced processes. So this is one reason why the Higgs is an amazing tool, is because in the standard model there's some couplings that show up at loop order. If there's new physics that's contributing at loop order, that's sort of leading order comparison to these standard model processes. Okay. So you can go ahead and you can measure this also at the LHC. So you can look at the size of the coupling of the Higgs to photons relative to the standard model prediction, and also the size of its coupling to gluons relative to the standard model prediction. So the diamond here is the standard model prediction. And you can again do a combined fit to these as you've inferred from the various production and decay modes of the Higgs. And you find within 1 sigma, it agrees pretty well with the standard model prediction. So again, this is a sign. This is a little discouraging. I think this is one direction where people certainly hoped that the Higgs would reveal evidence for new physics. That there could be new physics running loops, but that doesn't that's at least fairly strongly constrained given this. The other thing, this is important to follow up the most recent results. So for a long time, very early on in the LHC process of Higgs discovery, both collaborations had a very high coupling of Higgs to photons. So the central value was more like 1.5 at both Atlas and CMS. People got very excited about this. Then CMS measurement went way down to about 0.6. So then the average of Atlas and CMS was about standard model. And now in the final legacy analysis, CMS has come back up, but it's pretty consistent with the standard model value. So that's the story, yeah.
So just to compare, when you're talking about S&T, you said, oh, we knew ahead of time that the couplings were all going to be just the standard model. So that was specific, that's sensitive to the
massive gauge boson, the tree level coupling to massive gauge bosons. Whereas you didn't have, yeah.
So but you'd also in that table right before that when you showed all those included the boson coupling.
Yes, well. Yeah.
So that table that you showed before this one already had things that would not, so the 2 photons would have never been, that could have stayed high.
And been consistent with S&T being small. So for example, it's true that whatever loops ran to give contributions to S&T would have also contributed to diphoton or vice versa, but those things could have been totally consistent. So the fact that we knew precision electroweak variables didn't preclude this from being wildly off. And this just has to do, if you want to think of it in terms of the dimension 6 effect, standard model effective Lagrangian, basically you didn't know, until you had the physical fluctuations of the Higgs, you weren't able to constrain things like this, but you were able to constrain related operators that contributed to S&T. Okay. Something else that you learn just by doing this coupling fit is, so something you would worry about is that we produce the Higgs at the LHC, but it has additional decays to particles that are outside the standard model, and maybe we don't see them in the detector. So maybe it decays to some particle that acts as dark matter, and we just have no ability to pick up on that because the decay modes, those decay modes just are not distinct enough to be identified. So you could worry that there's some large width of the Higgs to new states that we're not sensitive to because we're not looking for them. So the first thing you could do actually is try to just constrain that with a coupling fit. So this was the first way that people tried to constrain invisible decays or beyond the standard model decays of the Higgs, which is just to say, let's imagine we infer all of the possible couplings of the Higgs to standard model degrees of freedom, and then we add into that an additional decay into invisible states. And now let's just do a combined coupling fit and see if we can constrain the possible rate for decays into these invisible final states. Okay? So there was actually a trick to doing this in the couplings, which is you have to ask that the coupling to massive vectors is not greater than 1. That's a reasonable assumption, again, based on Precision Lecture Week or also unitarizing vector boson scattering. And if you do that, then you can actually construct a fit and place a limit at about 60% on the branching ratio of the Higgs to invisible states. But this is a bit of a kludge because you had to bound one of the possible couplings. So if you take away this bound, there's then a flat direction where you can mutually scale up all of the couplings of the Higgs to standard model final states and add invisible branching ratio. And you simply can't constrain that flat direction until you make some assumption about the couplings, and then you can get some finite likelihood. Okay. So that's fine. This is sort of an inferential way of saying that we know the Higgs isn't decaying too much to invisible final states. But one of the really awesome things that's happened in the last the last part of run 1 is we've actually been able to place a direct bound on Higgs decays into invisible final states. So again, I said if the Higgs is decaying invisibly, that's something we can't pick up invisible decays on their own in the LHC detectors. But if the Higgs was produced in association with some other standard model final states, we can identify that associated production mode, and then we can just look for the fact that the Higgs itself didn't appear. Its decays were invisible. And so we can make that measurement. And in particular, the way you do that is you look for the production of the Higgs in association with vector boson fusion. So it has an association with 2 jets at the LHC. Or you can look for the Higgs produced in association just with the Z boson. And again, in either of these cases, you can pick up on the jets, and then there's some missing energy coming from the invisible decay of the Higgs. Or you can pick up, for example, on the leptons from the Z boson and identify there was an invisible decay of the Higgs. And so you can use this actually to place a direct bound on the invisible cross-section times branching ratio of the Higgs into invisible final states. So this plot was done as a function of mass. So the standard model Higgs is around 125. And this is corresponding to 100% of the production decays of standard model Higgs going invisibly. And so what you find is for standard model Higgs, the bound at CMS based on these measurements, the direct bound is about 60%. And at Atlas, the measurement is actually slightly better. It's about 50%. Okay. So this is beautiful. This is a direct statement about the size of possible ways that the Higgs could be decaying invisibly. There's a slight caveat. There's still sort of a flat direction. I told you in the coupling measurement, you could float all of the couplings and add an invisible branching ratio. You can also do that to a certain extent here. It gets a little more complicated because now you're also directly measuring the invisible branching ratio. But if you were really worried and really nervous, you could say it's possible the Higgs is doing very strange things. Maybe it has many more decay modes that are not accessible to us, and we don't know that, and we have a very hard way of pinning that down at the LHC. So the most beautiful measurement that's happened in the last 6 months was a great surprise, which was we've actually been able to place a bound on the total width of the Higgs directly. Okay. This is impressive because the total width of the Higgs is just summing all of the possible decay modes of the Higgs. That includes standard model final states. That includes invisible final states. That includes maybe something that's not invisible but doesn't look like a standard model final state. All of those things. And the reason why that's impressive is nobody thought you could do it at the LHC. Okay. At the LHC, when you have a Higgs, what you're measuring is its production times some branching ratios, and you never have absolute sensitivity to the width of the Higgs itself. Okay. And indeed, prior to this measurement, which I'll describe just momentarily, the best statement we had about the width directly was you can infer the width based on the experimental resolution of the Higgs decaying into 4 leptons. So that has some shape to it, and from the width of that shape, you can make a statement about the width of the Higgs. So the constraint that was arrived at was that the Higgs could not be wider than 3.4 GeV. The standard model expectation is about 4 megaelectron volts, so 3 orders of magnitude smaller than this, right? So at the LHC, basically, we only thought we could get within 3 orders of magnitude of constraining the standard model width. And there's now a measurement that gets us to within 22 megaelectron volts. Okay, so it gets us within a factor of 5 of the standard model value, and it's a 2 order of magnitude improvement over the previous bound. So the way this works, it's a very clever measurement. If you just look at, so the Higgs is produced most commonly at the LHC through the fusion of gluons. And then a very distinctive final state, of course, is where the Higgs decays to 2 Z bosons, and those Zs go into leptons. So usually what happens, of course, the Higgs is 125 GeV. 2 Z bosons are together about 180 GeV. So of course, a Higgs that's on shell can't produce 2 on-shell Z bosons. Usually what happens is the Higgs produces 1 on-shell Z boson and 1 off-shell Z boson. Okay? So that's the predominant mode of production and decays and disease at the LHC. But some very small fraction of the time, the Higgs itself is forced off shell, and then both Z's can be produced on shell. And you can identify that by basically looking at the invariant masses of leptons produced in the final state. Okay. So the way you put this to work is you make the following observation. So there's some differential distribution of the production cross-section of the Higgs from gluons decaying into Z bosons as a function of the invariant mass of the two Z's that it decays into. Okay? So this, of course, depends on the production cross-section of the Higgs and its coupling to Z bosons. And then it has some structure that's basically what is the invariant mass of the final state relative to the Higgs mass. And then it has some sensitivity, of course, to the finite width of the Higgs. So if you just take this differential cross-section and you integrate it in a little mass range right around the mass of the Higgs, and you compare that to a mass range well above the mass of the Higgs, what you see is, so that corresponds to on-shell Higgs versus off-shell Higgs. What you see is the on-shell production, that's sensitive to the width, okay, in some normalization. In that normalization, the off-shell production of two Z bosons, so the Z bosons themselves are on-shell, the Higgs has gone off-shell, that's independent. So now if you take a ratio of these other things that you didn't know about, maybe possible deviations in the production and decay couplings, they drop out. And you have a direct measurement of the width of the Higgs compared at least to the Higgs mass and to the mass of the Z boson, which is known very well. Okay, so I've slightly simplified how this measurement takes place. But basically what you can see heuristically, this is just a nice CMS simulation to show you what's going on. The red line, so this is a function of the invariant mass of the 4 leptons that came from 2 Z bosons. That's plotted down here. This is number of events from some arbitrary normalization. And so in the standard model, what happens is you get some big peak corresponding to on-shell production through the Higgs. That's where all 4 leptons come to reconstruct the Higgs mass. Then there's a drop. Then there's actually a standard model production rate for pairs of on-shell Z bosons. And then there's a drop after that in some long tail. So the red line is the standard model prediction. But then if you took the Higgs and you blew up its width, okay, so you increase the denominator there, but in some normalization where you're keeping the on-shell production fixed, what that tells you is now you get some big tail of on-shell Z bosons that are produced through an off-shell Higgs. Okay, so basically now you just look at this distribution in the standard model and you try to discriminate the standard model line from some vastly blown up line that corresponds to some big width. So that's how the measurement's done. It gets us a constraint that the Higgs can't be heavier than 22 megaelectron volts, and that's a beautiful measurement because nobody thought it was possible to do. We're within a factor of 5 of knowing the standard model Higgs width. So I find this very exciting. Okay. So the general take home, mass is converging on 125. There were some ups and downs in this battle, but I think it's getting tightened down. Both experiments measure couplings that I would say are too impressively consistent with the standard model prediction, but at least in line with expectations you had beforehand. And then the thing that's exciting is we know more about it than I think anyone thought was really going to be possible when we set about looking for it at the LHC. Okay. So the other thing I want to just touch on, I said I would tell you about the state of searches in the Higgs sector. That includes the standard model Higgs boson, but it also includes searches for other possible Higgs degrees of freedom that could be involved in electroweak symmetry breaking. Okay? So this is not sort of a just so story. In fact, there are many models of physics beyond the standard model. Supersymmetry is a canonical example, but there are many, many such models that actually predict that you could have a standard model like Higgs, like the one we've seen, plus additional Higgs scalars or pseudoscalars that would also exist around the weak scale. Okay, so it's strongly motivated from a theory perspective, but also, just from a sort of bottom-up perspective, we know the spin 1/2 and the spin 1 sectors of the standard model are very rich. So there's no reason not to wonder why we couldn't have the same diversity in the spin 0 sector, the scalar sector. And this is great. This is a great opportunity because, of course, we have standard model like Higgs searches that have been conducted at the LHC since the start of Run 1. But also now there's opportunity to develop new and even more exotic types of searches to look for these additional Higgs scalars. So the reason why this is interesting is that this was something that was not being done when we were pursuing the standard model Higgs. So there was an immense opportunity to go and look for it. And this at least is one aspect in which I've been involved in efforts at CMS. So examples of how you can look for extra Higgs states without doing any work. I told you one way we looked for the Higgs was in the Higgs decay to 2 Z bosons into 4 leptons. Of course, we do that around the mass of the Higgs we discovered, but you can in general look for those leptons at much, much higher masses. Okay? So that's a direct way. You can just keep doing the search you're already doing. You can just extend it out to higher masses. Both Atlas and CMS did this. This was sort of the canonical strategy going in. And the output is right now, they can look to very high masses, and both experiments find that the measurements are in pretty good agreement with standard model predictions up to very high mass. So this is one way of excluding additional Higgs-like scalars at very high mass. I don't want to bother you with the details of what's in this plot, but this is just showing you for some additional Higgs state, its couplings can vary across some parameter space, and just making these measurements actually cuts out a large range of that parameter space. Okay, so this is an effective measurement, and it's one that you could do without having to do any extra work. This is allowing you to probe the existence of additional Higgses at higher mass. So something that might be a little surprising to you is that that was not actually the strategy. You might think a good strategy is just to take all of the ways we look for standard model Higgs at low mass and extend them to high masses, because there could still be states that are sensitive in those channels. So one place where that actually took a lot of work, so this has only just happened in the last, I think, about 5 months at CMS and Atlas, is to also extend the search for Higgs decaying into 2 photons to very high masses. So it turns out in many models this is a very effective way to look for additional Higgs scalars. And it wasn't being done. And the reason it wasn't being done at CMS cut off their search for pairs of photons at 150 GeV, because the primary background of this search comes from QCD, and they could fit the QCD background with a degree 6 polynomial. And of course, degree 6 polynomial goes up or down at its endpoints, and they didn't want to have to extend the polynomial fit to higher masses. Okay, so that was the reason why they didn't do the search. And after a lot of efforts, we were able to get the search done to very high masses. So now we're also looking for diphoton resonances out to high mass, out to about a TeV. And the details depend a little bit on whether this additional scalar is narrow or wide. That changes, of course, the distributions of photons. But these searches are now happening at the LHC. And again, the axes don't really matter, but in some parameter space for extra Higgs scalars, you can rule out now large swaths of parameter space by doing this search. So this is an example of one direction we've started to push. We should have been able to push there earlier, but again, these searches are only in their infancy. And then the even more exciting things you can do very unconventional searches. So for example, now that we have a standard model like Higgs, if you have additional Higgses, one thing they can do, for example, if you have a very heavy Higgs, it can decay into pairs of the standard model like Higgs. All right? So that's a very interesting process, because the standard model rate for this is very low. This, again, wasn't a search that was being done at the time of the Higgs discovery, but it was a search that you could do as soon as you knew you had a standard model like Higgs. So one of the things that I did actually was to figure out that you could constrain this process using existing data. So I did that, and then I became an external collaborator of CMS to get the search done at CMS. So one way we went about doing this is you can have, again, this heavy Higgs scalar. It decays to 2 light Higgses. There are many possible decay modes of the standard model Higgs, and so you can look at them in various combinations, and you can use them to actually constrain this possible production and decay mode. Okay. So we started by looking at leptonic decays of the Higgses. Now, actually, there are 3 searches that are constraining possible heavy scalars decaying into pairs of Higgses that go out to very large mass. Unfortunately, right now, all the searchers are in pretty good agreement with the standard model prediction, but this wasn't something that was obvious until about a month ago. So it's a sign that, again, even within Run 1 data, there are questions we can ask that haven't been asked yet, and there are interesting opportunities, ways that we can use the Higgs to probe the existence of additional scalars. Okay. There are more examples of that, but I won't bore you with them. But the take home here was just that, I think it was very exciting to discover a standard model like Higgs, but there's no reason not to expect that the electroweak symmetry breaking sector could have rich structure. So there can be additional Higgs states we should look for. There's great complementarity between what we know about the Higgs we've discovered and our ability to look for these additional scalars. There are ways that we can do this without doing too much work based on existing search strategies, but there are also new searches that we're in the process of designing. So this is, I think, something, the efforts are still in their infancy. We've gotten some new searches to get done at CMS and Atlas, but there's still a lot we can do both with the existing data and with the data set to come. Okay? So this is something, however bad SUSY searches might look, there's a lot of room to look for additional Higgs scalars. Okay? So that's all I wanted to say about the Higgs. This being sort of an astrophysics seminar, the next thing I think to talk about is dark matter. And the reason why dark matter is interesting to talk about is if you look at the plots that are disseminated by the collaborations, they'll show you plots which look like the normal mass times nucleon cross-section exclusion plots. They even have the audacity to show exclusion curves coming from direct detection experiments. And then they overlay across these exclusion curves the CMS and Atlas exclusions, which look extraordinary, right? So this is spin-independent cross-section. So again, here's Lux, here's Xenon, CDMS, Ku. And then you see these CMS lines that have interesting properties. So one is that they extend, of course, to very low masses. The other is that they seem to be, they depend on some operator that I've identified to set this limit, but they don't seem to depend on any other properties of the dark matter sector. And in particular, there seem to be exclusions that are extending down to be competitive with or better than existing direct detection searches. Okay? And the same thing is true also in spin-dependent dark matter. So now you can have spin-dependent couplings. And again, the limits that CMS and Atlas set beat most of the existing direct and indirect detection limits that we can use to set bounds on dark matter. So you might just say, looking at these plots looks pretty great, right? So who needs direct detection? The LHC is doing fantastic. And I mean this as a joke, but in terms of funding discussions, there are serious people who've looked at these plots and actually concluded that there's no need for example, for low mass direct detection. So it's worth piecing apart exactly what is going into these plots and why this doesn't mean that that dark matter is just being systematically excluded by the LHC. Okay.
Are you talking perimeter reactions?
Am I talking about perimeter? No, I know. Yeah. So of course, so how are these searches done at the LHC, right? So the way that they do them is to work in some effective operator paradigm. So you can see again from these plots, each one of these curves comes with some operator. So the operator is a little hard to read, but this operator here is what they would call some vector operator. This is some scalar operator. This is some axial vector operator. Okay. So those operators, they involve the dark matter particle, which in this case is just assumed to be a fermion, and then they involve some coupling to some standard model gauge invariant quantity. So for example, you can have a scalar type coupling between pairs of gluons, gluon field strength. Of course, this is an irrelevant operator, so it's suppressed by some mass scale. Similarly, you can have this vector coupling. This is the vector coupling involving dark matter fermions and just, for example, QQ bar. That's also suppressed by scale. And then you can just have the axial vector coupling, which involves additional insertions of gamma 5. Okay. So these all correspond to some effective operators, right? So there's some effective operator where the effective operator is a blob. It's attached to quarks or gluons, and then it's attached to dark matter. And of course, if you turn it this way and you look at the LHC, now you can't normally just look for invisibly produced particles, but just as you were looking for an invisibly decaying Higgs, if there's some other radiation in the initial state of the process, like a gluon radiating off the quark, you can trigger on that. Then you can identify that there was some missing energy involved in the event, and you can place a limit on the size of this effective operator. Okay? So then, of course, once you have that, now you can turn this diagram on its side. The coupling of that diagram is still the same, and so you can translate it directly from an LHC bound on these effective couplings. You can translate it directly to a dark matter nucleon scattering limit. Okay, so that's how you can end up plotting for some given operator. You can take some exclusion that you can set at the LHC, and you can then just translate it directly to the dark matter mass nucleon scattering plane. Okay, so it seems like a fairly simple proposition, and that's how these plots are made. But of course, the natural question you can ask is, where do these effective operators come from, right? So this effective operator has some mass scale associated to it. Really, it's some mass scale with some couplings involved. That came from some massive degree of freedom that was integrated out to give you the effective theory. So you can ask the question, under what circumstances do I care about that massive degree of freedom? Do I care about its couplings? Under what circumstances is this whole picture of effective operators consistent with the bounds that I'm claiming to set at the LHC? So a simple way to probe this is just to take apart that operator. So to take this operator, which is some effective point interaction, and blow it up by putting the S-channel exchange of some scalar degree of freedom in there, or vector degree of freedom in there. Okay, and so there are two things that you can pick out immediately, right? One is this degree of freedom has its own physical mass, and so the mass scale of the effective operator that you're placing a constraint on, that's some linear combination, that's some fraction involving the mass of the scalar particle and its couplings. And then the other thing, of course, that pops out is the amplitude for this process has momentum dependence. So of course, if you're at momenta that are very low with respect to the mass of this particle, then the effective operator description is good. But if you're beginning to operate at momenta that are comparable to the mass of this particle, then now, of course, you actually have to worry about the non-trivial momentum structure of this amplitude. Okay, so you can take this simple picture where you've taken one operator and you've blown it up by integrating in the intermediate particle, and you can now look at it and you can see what happens to these beautiful limits that we set at the LHC just using the effective operator when we actually include the effects of this massive degree of freedom. So in particular, you can make a plot of the mediator mass, this physical mediator, versus the bound that you would set on lambda. So lambda is, again, this combination of its mass and its couplings to quarks and to dark matter. And so the way to look at this plot is to first focus over here. So this is a very high mediator mass. So at very, very high mediator mass, the momenta that's involved at the LHC is not large compared to this mass. So you expect the effective operator description is good. We can ignore the momentum dependence of the amplitude. And so in fact, that's what you see is the bound is flat at very high mass. Namely, there are no finite momentum effects that are changing the limit. But when you're so this is where you would say, OK, the ability to ignore this propagating particle was good. But now you can ask, okay, what is the actual bound I set for a particle that's out at 10 TeV? Okay, so the physical mass is at 10 TeV. You see the bound on the scale lambda is at about a TeV. But the only way to get from a physical particle of mass 10 TeV to a scale lambda of a TeV is if the couplings of this particle are enormous, right? In particular, if the couplings of the particle are about 10, then this is sort of a sensible statement to make, right? But if the couplings of the particle are 10, that's not a perturbative degree of freedom. So you really had no right to actually even integrate out a single particle or to say that your effective field theory is described by single particle exchange. That's just a bad assumption. So here in this corner where your effective operator description seemed like a good idea, the actual couplings that are inferred from the bound are non-perturbative, and you really shouldn't be able to say anything out here. Okay. So now what happens is you're moving the mass down. Of course, as the mass gets low, now you're at momentum at the LHC that are comparable to the mass of the particle. So you can have some resonant production of the degree of freedom. And here you find as you go through this resonant region, what happens is the bounds actually get better relative to what the effective operator description was saying. And that's just because this momentum dependence is shrinking denominators. It's increasing cross sections. And so your inferred bounds are getting better. Okay? But the thing that you worry about is once you get out of the resonant region, now you get down to areas where the mediator mass is light. For example, it's light with respect to momentum exchanges at the LHC, or even light with respect to the mass of the dark matter particle itself. And here what you see is happening, of course, is the bounds are getting much, much lower than the bounds that you were able to infer from the effective operator description. Okay? So the bounds are now much, much smaller than the effective operator description is telling you. And what's worrisome is this is happening right around 100 GeV. So what's around 100 GeV? 100 GeV is the exchange of any standard model particle that you thought was giving some weakly interacting massive particle its interactions with the standard model. Okay? So all of our canonical WIMP candidates, right, the mediators in the standard model are down around this region. And in this regime, of course, this effective theory description is completely irrelevant. And it's strongly overestimating the constraints that are placed by the LHC. Okay.
Should also be directly observable.
And the mediator, well, it depends on its, yeah. So that's not always guaranteed to be the case, right? So certainly you're not even, yeah. So you worry in particular about the 4 fermion operators. So the problem is most of those operators themselves, they just get buried in QCD, right? So most of the time you take a QCD operator, you do it on both sides, it's very hard to see. So the mediators are not guaranteed to be directly observable, but the take home is just that in both of the regimes, you know, in the regime where you think the effective field theory is a good description, the perturbative idea is breaking down completely. And in regimes where we expect weakly interacting dark matter to have its mediator, this description is also breaking down. Okay, so this is the big problem with what happens when you get exclusions coming from LHC bounds. The reason why they don't do it any better is that it's beautiful and seductive, right? That because you can just take this effective operator and rotate it, and you can take an exclusion from the LHC and put it directly on the mass nucleon cross-section plane without any extra assumptions, right? That's beautiful. But it's very wrong. And that's the real problem with looking at these plots. There's even more complications when you try to integrate in a mediator. So again, the example I was showing you was the momentum dependence for the S-channel exchange of a new degree of freedom. But if it has standard model quantum numbers, you can also, for example, have T-channel exchange. And so now the momentum dependence is very different. And so there's not even a simple inference. You can't simply take every effective field theory operator and blow it up in a simple way. Any given operator has multiple ways to blow it up. Okay? So you can see if you try to treat this problem honestly, it rapidly gets out of control. There are other ways to illustrate that. Catherine Zurich has also been making this point very strongly. They basically show you, without going into too much detail, this is what the effective field theory bound would be, and here's all the possible different other bounds you can get as you vary the way the particle is exchanged or its mass relative to the dark matter candidate. Okay, so as you can see, there's a huge change in what the limit space is as you actually try to flesh out this picture in detail. Something that it's basically, in almost every regime, it breaks down, yes. Yeah. So I think it really, it was good. It was good. I mean, there are some regions where, you know, it wasn't always guaranteed to be the case that when you were in this effective field theory valid region, the couplings had to be big, right? There are areas where the bounds are big enough that the couplings can be perturbative. So in those corners of parameter space, this is good. But those just turn out to be very small corners of parameter space. Okay. Something that is nice, so far I've been focusing on, imagine that you have these operators and you radiated, for example, off a gluon from the initial state of the LHC. So that's looking for a jet plus missing energy. One thing that's happening now that's very beautiful because it extends our sensitivity in lots of directions. It didn't have to be a jet. So you could actually have a Z boson radiate off quarks in the initial state. You can even have a W boson radiate off initial state. Photons, it's something that's particularly interesting. You can even have a Higgs radiating off the initial state or the final state. So you can look for any of these things that are produced in association with missing energy, and you can constrain different classes of scenarios, different types of operators. Okay. So again, it's not worth going into in great detail, but in certain circumstances, these other standard model initial states, so something like a W or a Z instead of a jet, they can actually give you better limits than just looking for jets. Okay. There's a slightly orthogonal range of inquiry that's happening right now that's very interesting, which is, of course, again, now we know there's a Higgs. Okay, so this is setting aside this effective field theory paradigm for constraining dark matter. We know there's a Higgs, and one very, a very consistent thing you could believe if you had weakly interacting dark matter is that the interaction cross-section between dark matter and the standard model is just coming through the exchange of a Higgs. Okay, so ignoring the CMS limits now, you can just look at the direct detection limits. So here's lux, here's xenon, and of course we know that unconstrained interaction of dark matter with the standard model through Z boson, that's way up here. That's already badly excluded by many experiments. But you could now have dark matter that's interacting primarily with the standard model through the Higgs, and the cross-sections for these processes can be down here in the regions that lux and xenon have yet to probe. So a consistent way of believing that, for example, we have weak-scale dark matter that is interacting through the standard model through a weak-scale degree of freedom is to imagine that it's doing so through the Higgs. The other reason why this is just a nice thing to believe is, imagine you have dark matter. It carries no standard model quantum numbers. So it turns out there is one marginal operator you can write down between a completely neutral degree of freedom and something in the standard model. And that's simply the Higgs squared scalar squared operator. So this is a marginal operator you can write down. It's consistent with gauge symmetry of the standard model. And so this is a leading way that new physics that has no standard model quantum numbers can couple to us. So apart from your beliefs about weakly interacting dark matter, this is sort of a leading way that new physics can come and talk to us. You can also have other things like fermions and vectors talking to us through the Higgs. These are not marginal operators in the same way. In particular, neutral fermions coupling to the Higgs, that's an irrelevant operator. And even though I've written this like a marginal operator, vectors coupling to the Higgs also come through some irrelevant operator. Okay? But this is a very consistent thing to believe, that dark matter is coupling to the standard model primarily through the Higgs. Now that we have the Higgs, we can start to ask whether it's possible using Higgs properties to place constraints on dark matter scenarios of this sort. And the beautiful statement is, of course, if the dark matter is lighter than half the Higgs mass, then the Higgs can be produced and just decay into this dark matter. And the fact that we look for that, so again, I mentioned the CMS search that's looking for invisible decays of the Higgs. The fact that we can now place a direct constraint on that means that we can directly constrain these scenarios. So again, under the hypothesis that dark matter is a scalar or a fermion or a vector that's coupling to the standard model directly through the Higgs, the fact that we don't see invisible decays of the Higgs boson translates to exclusions that we can place in parameter space of dark matter for dark matter candidates that are lighter than half the Higgs mass. So again, this is the Higgs mass. This is the usual DM nucleon cross-section. And so this line is 63 GeV. So this is right as the Higgs can decay into these dark matter particles. And the region depends on whether it's a scalar or a fermion or a vector, but the region above these curves in each case is the region that's excluded just by the fact that we have a bound on the invisible width of the Higgs. Okay? And what's beautiful about that is it's very complementary to the exclusions that we have from things like lux and from xenon. Those are excluding things at high mass and they fall off at low mass. And particularly now, the fact that the Higgs doesn't seem to be decaying invisibly, that's actually allowing, in these scenarios, for you to say complementary things about the low mass region. Okay, so this is something that's very beautiful. The only assumption that goes into this is that dark matter is interacting primarily through the Higgs, and it's lighter than half the Higgs mass. So this is a much safer exclusion to plot. Of course, it's still sensitive to assuming that this is how dark matter couples, but this is a beautiful example of how, now that we've discovered the Higgs, we can say non-trivial things about dark matter by exploring Higgs couplings. Okay.
What's the solid black line?
The solid black line, oh, this is yeah, sorry. So the dashed is lux, and I think this dashed region is some sort of, well, they've dashed Ku. So there, yeah.
The line is just, okay.
Yeah, it's a funny, okay, so I actually don't know what the Ku line is showing, why in particular it's dividing in a region. So, okay, that's, that I can't type.
And this maximum lattice for the
Oh, so this is, of course, there are some assumptions. If this is your interaction, you have to know exactly how the Higgs is actually coupling to nuclei. Okay, so some of that comes from lattice parameters. And so depending on the various parameterizations that you use to determine, to infer, so unlike, well, the effective operator description where you were coupling directly to constituents of nucleons, so there was less uncertainty into what the inferred nucleon cross-section was. Here, now you have to assume things about how the Higgs is coupling to the nucleon, and in particular, all the details coming from, for example, lattice parameterizations. So that's what gives the error bars.
So the min and the max, I should interpret as error bars.
Yeah, that reasonably they're the error bars, and the central value is the sort of central lattice determination. Okay. So what's the take home with respect to dark matter so far at the LHC? I think there has been considerable progress on ways that we can constrain dark matter scenarios at the LHC, particularly now that we've discovered the Higgs. This is a particularly cool way to constrain dark matter. But as I hope I've convinced you, the effective operator approach that is dominantly used now, it's simple, and it allows you to make direct comparison with direct detection, but we've rapidly reached the limitations of this paradigm, and really you shouldn't place too much credence when you see LHC bounds and direct detection bounds plotted on the same axes. So what's needed now is a new systematic program to somehow address dark matter searches at the LHC with dynamical mediators. Okay, and this is a very complicated and rich subject, and it's currently the matter of power struggles at both collaborations, but so I don't know how the story is going to turn out.
So when you said see them on the same axis, you should be cautious. That wasn't true of your Higgs plot.
Well, it is, yeah. So the Higgs plot, it's very clear. So the very clear assumptions are these are the ways that each of these degrees of freedom you assume is interacting with the standard model, and you assume that that is the portal through which.
So if I see a plot like this, then that specifies a type of mediator.
Yeah, so if I have a propagating mediator in particular, yeah. So then you know the dynamical information that's being used to set this bound. You say go for it. Okay. Okay.
But can you say regarding the systematic program, what do you expect them to do? To study
integrate things, yeah. Integrate in particles. So yeah, the simplest thing to do is integrate in some T-channel exchange, right? And then, of course, now that has standard model quantum numbers. So now you simply overlay the simplified model searches for direct production and decays with the dark matter inference. You do the same with S-channel. That covers a large class of simplest operators, right? So again, it's not complete coverage, and there are caveats then associated with the interpretation, but that's the correct thing to do. So. Okay, and so I just want to finish with the blog bit of the talk, which is to talk about, again, the tone that I think you hear from the LHC right now is Higgs discovery, it's standard model-like, everything else is standard model-like, phenomenologists go home. So I just want to cover at least what I think are interesting anomalies to be attentive to, and also maybe anomalies that you've heard about that may or may not be worth thinking about in greater detail. So a big anomaly that's gotten a lot of press, I think there was a Scientific American article on this, or a New Scientist article on this recently, was an anomaly in something that's sort of very banal, which is the WW cross-section in the standard model. Okay? So this is not a search for new physics. There's no missing energy. There's no propagating additional degrees of freedom you're sensitive to. You're simply measuring the productions of pairs of W bosons at the standard model. And you'd think pairs of W bosons, we have a pretty darn good prediction for that. That's a pretty straightforward standard model process. So it should be something that we should be able to pin down pretty well. And it turns out, actually, both collaborations, the measured cross-section is coming out high. So these are each the sort of summary tables of standard model diboson cross-sections at CMS and ATLAS. And the thing that I've tried to highlight here is this is the most recent WW cross-section measurement at CMS. And this is the same thing happening at ATLAS. And ATLAS is about 2 sigma off. CMS is about 1 sigma off. But the systematic error bars associated with this measurement, the number is much larger than you would expect the systematic to truly be. So you could be concerned that actually the discrepancy is bigger than this plot suggests. Okay, so each one of these is sort of a 2 sigma discrepancy on its own, but you could imagine in some optimistic space that this is growing into a 3 sigma discrepancy at 8 TeV, and maybe this is a sign of new physics. So a lot of people have taken this in various different directions. Basically, the idea is what could be explaining this is you have the standard model process, but you also have some very subtle new physics whose decays look mostly like standard model W boson production, but maybe have a little bit of extra stuff that we're just not really picking up enough to discriminate it from the standard model contribution. Once you add these two together, they would give you a total inclusive cross-section that's bigger than the standard model prediction. So Patrick Mead in particular has been pushing the idea that you could have supersymmetry and you could have fermionic partners of the W bosons they actually decay into W bosons and missing energy. And if they're not much heavier than the W boson, when they're produced and they decay, they look an awful lot like pairs of Ws. Okay? So he's gone to great pains to illustrate that if you inject this signal into the standard model cross-section measurement, it actually helps to fill in all of the discrepancies between the standard model observables and the theory predictions. Okay? So that's the beyond the standard model optimism for what this means. In reality, this is an anomaly that I don't think is worth paying attention to. And the details comes down to some very painful facts about making predictions for standard model cross-section measurements. So you probably don't ever want to care about this. But there's something very special about the WW cross-section measurement, which is that you really want to make sure if you're making that measurement, you cut out standard model backgrounds to WW production. And in particular, one way you do that is you veto events, you throw out events that have additional jets in them that aren't attributable to standard model WW production. Okay? So that means in these events, you identify some set of jets you don't like, and you throw out events that have those jets. But in particular, when you impose that jet veto, that introduces a new scale into the problem. Okay? There's the scale of the W bosons, and then there's also the scale of this jet PT veto. Now there are two energy scales, and if you do a fixed order calculation of the cross-section, which is what the theory predictions start out as, those fixed order calculations, you don't know what scale you evaluate those fixed order calculations at, because now you have the mass scale of the W bosons, that's usually the right scale to evaluate in, but you also have the mass scale of the jet PT cut. And if you don't account for that accurately, actually, you get large logarithms of the difference in the scale, and that throws off the precision of your theory prediction, or it throws off the interpretation of your standard model cross-section measurement. Okay? So there's some very careful work done by a couple of authors to actually resum these logarithms and improve the precision of their standard model theory prediction. And what they find is once they do that, actually, there's basically a small 1 sigma discrepancy left over, and everything else is consistent. Okay. So this is an anomaly that's gotten a lot of press lately. I think the answer is it's all standard model.
Does the other group agree with that?
Does Patrick Mead agree with that? I don't think Patrick has taken the time to delve into the resummation calculation yet. I certainly believe that this is the correct explanation. Did Patrick? No. Well, oh, sorry. Well, Patrick. Okay. This resummation calculation, right? I would call this a very careful. I mean, they did the nice sket calculation. They ordered the calculation very well. They demonstrated insensitivity of their final result, right? Whereas I don't think what Patrick, and in fact, I mean, this author is common between the anomaly explanation and the jet veto explanation. So I'm tempted to believe this is the explanation, but yeah, I'm sure Patrick believes otherwise. Okay. The other, I think, over the summer, the other excess that has gotten some amount of press is some excess in CMS in pairs of leptons and pairs of jets. So this is some heavy resonance search where basically they look for pairs of electrons and pairs of jets that came from some initial parent state. And so, of course, if you look at the energies and momenta of these electrons and the jets, they all reconstruct the invariant mass of some common progenitor. And so there's some standard model background for this process that's smoothly falling. And so they look at all these different bins as a function of the invariant mass. And then there's one bin where it's very high. So you can see here there's about, I guess, 8 events that's fairly discrepant from the standard model background. And locally, this is about a 2.8 sigma excess. I would say my take on this, whether this is a sensible anomaly or not, this is not a sensible anomaly. It's one high bin, right? We look in lots of bins. This one happened to be high. You can imagine there's some heavy resonance decaying to these states, but I think this is something that I at least am not putting a lot of credence in. Things I put a little more credence in. So when I was telling you about how all of the standard model production and decay modes of the Higgs were lining up very well with the standard model prediction, there was one bin that was discrepant by a few standard deviations, and that was for top associated production of the Higgs with the decay into W bosons. Okay? So that's a very interesting process. It's a pretty rare process relative to other standard model production and decay modes. It's also interesting because whether or not you thought a Higgs was actually involved, it's sort of an interesting final state. It involves top quarks and W bosons. These are also things you can get out of supersymmetry or other models for physics beyond the standard model. And the measurement they make of this, of course, they don't actually know that this is what's happening. But what they do is they go and they look for pairs of leptons that have the same sign. Okay? And the way that you get that from a process like this is the tops are produced with opposite charge, and the W's are produced with opposite charge. But the tops and the W's can decay in ways that give you no leptons or that give you leptons. So what you need is the top and the W that have the same sign to decay into leptons, and then the top and the W with the other signs to decay into something else that doesn't have an easily read charge like a jet. Okay? So in those events, you get 2 leptons that have the same sign. This is a process that has a very low standard model background. They also ask for a large number of jets because there's a lot of sort of jet activity in the decays of the state. They ask for 2 bottom quarks coming from the decays of the tops. And then they identify the fact that these W's came from Higgses by using a boosted decision tree, which basically that's where they train a neural net or something like a neural net to discriminate very subtle kinematic differences between W's that came from the Higgs and W's that came from something else. Okay? And so when you apply all these things to the data and you look and compare your measurement of this final state to the standard model prediction, what you see is you get about a 2.5 standard deviation discrepancy from the standard model prediction. Okay? And you can sort of look at the invariant mass distribution. You can ask, again, is this a single bin thing? Is just one thing going high somewhere? Or is it some sort of systematic difference? And the answer is it's sort of a systematic difference. You can look, for example, as a function of jet multiplicity, and bins are a little bit high relative to the standard model prediction. So that's an interesting excess. The other thing you ask if you have an excess like that, is it consistent? Okay? So in particular, if CMS has an excess, does Atlas have an excess? Well, right now, Atlas doesn't look at this. Okay? So they've done no search that's trained for this particular process. You can also say, looking at CMS and Atlas, they do other searches that involve similar final states. And so are those final states high? And so, for example, at CMS, this bin is the final state in their other same sign dilepton search that's relevant to this process. And you see in various high and PT jet areas, they're high. Okay, so this is the same bin. This is the same bin that you're interested in. They also turn out to be high. So that's interesting. All right, that's consistent with there being something excessive going on in this way. Atlas doesn't have quite as glaring excesses, but also in relevant categories, they're high. Okay, on the tails of some of their distributions. So I'm not claiming this is evidence of new physics, but at least there's a consistent excess that, as far as I can tell, every channel where you'd expect to have sensitivity to it is showing up high. And the final state has something to do with top quarks and W bosons. Okay. The other excess that I think is really interesting, this is actually a 3.5 standard deviation excess. The joke here is this is a new color discovered at the LHC. So the reason I say that is all the exclusion plots that are quoted at the LHC, they have some Brazil band, which is the 1 and 2 sigma error bars. And you end up with a plot that actually has orange. So that's the 3 sigma error bar. And the central value of the measurement is outside the 3 sigma error bars. Okay. So this is the discovery of the color orange at the LHC. So what is this? So this is an interpretation of a search for events with 4 or more leptons at the LHC. And in particular, the particular interpretation which this is plotted is for some process where you have supersymmetry and you have scalar partners of leptons that are produced, and then they decay in some sort of cascade that throws off multiple leptons and then ends with a little bit of missing energy. Okay? And so if you apply this interpretation to the data sample with 4 or more leptons, you find there are regions where you have this large discrepancy between the number of leptons you observe and the number that the standard model predict. So you can actually trace it down to where the bins where this is going wrong. And there's sort of a very special configuration of 4 lepton events. There are lepton events that don't look like any of the leptons came from a Z boson. There's 1 tau involved in these 4 leptons. There's no bottom quarks, and there's not a lot of other jet activity. So that's a sort of characteristic of this physics. And then within that category, you can ask, what is the missing energy distribution? For example, as I ask for more and more missing energy, what do I get relative to the standard model? And the answer is, what's interesting about this excess is they're consistently high. Okay, this looks like if I took a distribution of missing energy from some new physics and injected it, it would in fact give me bins that are high as I go across. So that's why this gives you such a large discrepancy. No single bin is particularly discrepant with the standard model, but of course the signal interpretation is a much better fit than the standard model background. Okay, so that's why this is a 3.5 sigma excess. As with the TTWW excess, you can ask, is this consistent? So one thing that's interesting is that they had the same excess at 7 TeV that they now see again at 8 TeV. It's also consistent with all other searches you could do for the particular scenario they propose. So that's good. It's not ruled out by anything else. Whether Atlas sees it is a tough call. And it's the reason Atlas doesn't see it or isn't in a position to say that they see it comes down to cultural differences. Atlas also does a search for 4 more leptons, but the way that they bin it is more inclusive than CMS. And so basically, the CMS bin is some combination of events in this bin and in this bin, but they're projected onto each other. And so you can't actually say if Atlas is high in the relative bin or not. Private communication is that Atlas is not high in the relevant bin, but I don't know how to weight that. Okay. The last thing I want to say before I go too far over, there's one last thing that's gotten a little press recently, which is a 2.6 sigma excess that actually started out as about a 4 sigma excess at CMS 2 years ago. And so the reason why I point this out So every time a physics analysis is done at Atlas or CMS, it gets an analysis number. And the analysis number starts with the year in which the search is carried out. And then the number of analysis it is. Okay. So the analysis was a SUSY search, and it was started in 2012. And the first results about it were posted at the end of August in 2014. Okay. So that's interesting because that tells you they started doing the search in 2012. They had almost all the data. They held on to it for 2 years, and now they finally released it. Okay. And the reason for it has to do with the fact that in 2012, this was about a 4 sigma excess. And now, at the end of the day, it's down to about 2.6. So what is it? It's sort of a funny measurement. So in addition to just looking for numbers of states beyond standard model predictions, you can look for kinematic features. And one classic kinematic feature that you see in supersymmetry is you can have a process where a particle is produced, and it decays through another particle. And so the initial decay shoots off a lepton. That second particle decays, it also shoots off a lepton, and then maybe it goes to missing energy. And if this particle is lighter than the mass splitting between these two states, you can look at the distributions of these two leptons, and they'll actually make a triangle. Okay? And the endpoint of the triangle is equal to the mass splitting between these states. Okay? So this is a canonical signature of supersymmetry. Even if this particle isn't on shell, if it's heavier than the mass splitting, you still get a peak that sort of has an edge, but it's not as distinctive. Okay? So that's nice because that's now a kinematic feature that you can use relative to the standard model. And it's very hard to pick out of this plot now. It doesn't look very distinctive. But the excess is coming from the fact that basically you can inject this triangular feature into an excess that's just below the Z mass in leptons. So the peak is around 78 GeV. That corresponds to a splitting of about 78 GeV. And again, it doesn't look very distinctive in the residuals. But at the end of the day, it's sufficiently distinctive that it's about 2.6 sigma. Okay. So is this an excess? Something that's sociologically interesting about this is Atlas doesn't yet have a search for it. The search, Atlas has just now started their search. The search has been started by a former CMS postdoc who actually was involved in the CMS search. So it remains to be seen what Atlas has to say about this. Other possible ways that these decays could be happening that you would look for in other final states are more poorly constrained in this analysis. So this is the best way to look for it. The simplest explanations are ruled out by the direct limits, and the significance has fallen off over time. So I don't know what to make of it, but it is sort of interesting, worth paying attention to. OK, so the takeaway here is there are a small handful of excesses beyond single bin fluctuations that are somewhat consistent. So in particular, things like multileptons, this top Higgs-associated production excess, maybe this dilepton edge. They're promising. They're consistent. I would call them sensible excesses. I don't know if you agree that that's a good standard for sensible excess. What do these events have in common? They have something to do with leptons, some third generation activity like bottom quarks and taus. This could either mean there's some consistent new physics origin, or we have some systematic problem with our backgrounds. OK. All right, so with that, I just want to bring it to a close. I tried to cover what I think are the most interesting things that we've learned from run 1, and also the more interesting things going forward into run 2. The Higgs is looking very standard model-like. There's still a lot of room for surprises, though, and there's a lot we can do to improve our coverage of the Higgs sector. Dark matter searches are, this beautiful program for dark matter searches, the LHC. They're very complementary to direct searches, but they really need strong development beyond current effective field theory description. And you shouldn't believe at face value most plots you see that overlay these LHC results with dark matter direct detection. And then finally, in the optimistic phenomenologist category, there are some consistent anomalies. There are not as many 2 to 3 sigma anomalies as you would expect, given the number of measurements we've made. But there are at least a few, and the few that they've let us look at are all fairly consistent with themselves and with other measurements. So these are worth keeping an eye on, although not worth writing papers about. But I think run 2 should be a whole new adventure. Things start up in April of next year. We should have interesting results in times for the summer and the fall conferences. We should be getting around 50 inverse femtobarn per year for the next 3 years. So that's going to recapitulate the whole run 1 program really within the first 6 months, even before the first 6 months of running at run 2. So that means we have a lot of progress to look forward to. So thanks very much for sitting through this, and please ask me any questions you might have.
Questions?
OK.
So you didn't talk about supersymmetry, but I guess I'll ask sort of vaguely. Overall, what's the status of trying to solve the naturalness problem with the current results from the LHC?
Yeah, good. So this is my one backup in case there's a supersymmetry question. So the thing to focus on, if you're really interested in naturalness, of course, the story that we have shaped during the first run is that all superpartners are not created equal. So in particular, if you're interested in the sensitivity of the weak scale to the mass scale of new superpartners, the ones that you need to be light in terms of the sensitivity of the weak scale, you need partners at the top quark, you need the stops to be light. Okay, those are the most important things. But also you need things like the partners of the gluons to be light, the gluinos to be light, because they have some radiative input into the weak scale. So that's the area, if you want to ask about naturalness, that's the area we focus on. And then this is not a good way to show the limits, but the bounds that are now being set are stretching out to the vicinity of about 750 or 800 GeV. And if you just ask, so that's just looking for stops, and it has the most pessimistic range of the bound is assuming that it's decaying into a massless invisible particle, so that's the best limit you can possibly set. As the lightest supersymmetric particle gets heavier, those bounds get a little bit worse. But if you just say how natural is supersymmetry with a stop at 750 GeV, the answer is it's about 5% natural, 10% natural, just from that state. Okay? You throw everything else in, you try to write down a complete model that's consistent with all this, it's less than 1%. Now, what does 1% mean? I don't know. I think everyone thought that supersymmetry could have been 100% natural before the LHC, so that means we're 2 orders of magnitude down in some measure, but it's not clear what that means. I'm not giving up on supersymmetry yet. I still think there's a long way to go before we should be nervous about supersymmetry, but so far there's been no particularly encouraging positive results. That said, these anomalies that I'm pointing out, some particular ones that involve tops and W's in the final state, these are ways that very subtle supersymmetric configurations, particularly involving stops, can show up. Okay, so in particular, you can end up in configurations where missing energy is being extinguished because of the kinematics of the event, but you are sensitive to these final states, and they can actually feed into these anomalies that I've been describing to you. So, you know, I think there's a lot of room for supersymmetry. I'm not going to give up on supersymmetry yet, but I've gotten tired of giving talks about the state of supersymmetry and having people, you know, say that supersymmetry is dead. So that's why it wasn't a big feature of this talk.
What is the SMS framework? I'm just reading the discussion.
That's the standard model scalar. That's the BEH. Yeah, that's right. So sorry, this is historical contingency of Brown and Angler. Well, not being sure what to call the Higgs boson. Okay. So.
Do you have an idea for what is the difference between constant TT Higgs anomaly?
You know, I haven't thought about it in great detail. What's slightly funny, I mean, it doesn't have to, so yeah, so obviously it's leading, something in the BDT, something in this boosted decision tree is finding the WW events to have the kinematics of a Higgs. Okay. So there's something about scalar production of a singly on-shell and an off-shell W that's tempting. But as I think I showed you, just the same sign dilepton searches with the same number of B-jets not using the BDT, those also have excesses. So I think anything actually that has some third generation component that's producing same sign dileptons, you could end up with some sort of stop Chargino scenario, right, where that's the final state you're getting, but for some reason the kinematics is squeezed, so there's not a lot of missing energy. That, I think the first place that would show up is actually in this TTWW final state. So that's, but of course I have SUSY blinders on in my model interpretation, so that's why that comes to mind. Yeah. I should also say, although I didn't, you know, if you thought that the WW cross-section excess was an excess, another explanation is very light stops that also are decaying through Charginos, and that's all compressed. So that's another consistent explanation. Yeah, there's probably some conspiracy theory where these things are all the same thing. Yeah.
Well, in lieu of the time, we should thank Nathaniel again. He's here today and tomorrow, and he's on the 14th floor if anyone knows.
Okay, thank you very much.